Hello guys, this is Professor Alexey Shenkarenko from the University of Brasilia, and I'm starting a set of lectures in aerodynamics and in gas dynamics in order to help my students in aerospace engineering department to study better these subjects. My discussion in aerodynamics and gas dynamics will be based on a book of Anderson, Fundamentals of Aerodynamics, 5th edition or 6th edition. The structure of the course is based on incompressible flow in aerodynamics, and for gas dynamics is compressible flow theory. First of all, we study some introductory thoughts. It's a first chapter of aerodynamics in the book, and it's the biggest chapter that we have. And this is why we will spend most of the time studying this part. Then we will talk about fundamental principles and equations, things related to building of mathematical models for incompressible flows, fundamentals of inviscid incompressible flow, where we elaborate the models of Laplace equation, and we try to solve simple cases of these flows. Incompressible flows over airfoil, where we discuss theory of thin airfoils and cambered airfoils, trying to apply Laplace's equation for real airfoil structures. Then we talk about flow over finite wings, where will be introduced question of three-dimensional flow around the wing with side effects. And at the end of the course, we will talk about three-dimensional incompressible flow model and introduction to numerical techniques based on solution of Laplace's equation. The course of aerodynamics has 60 hours of lectures and 15 hours of practical classes. Practical classes are a solution of numerical problems in ANSYS Fluent, which I recorded separately, and you can find them on my channel as well. During study of aerodynamics, you will need to make 3 works. Work 1 is about study of the airfoil properties. It must be delivered at 1/4 of the course. Work 2 is devoted to simulation of inviscid incompressible flow around the airfoil. It must be delivered at 65% of the course. And work 3 is about numerical simulation of viscous incompressible flow around the airfoil. It must be delivered 1 week before end of the course. Here you can see a list of books which I recommend you for studying of aerodynamics. The main book we will use is Fundamentals of Aerodynamics of Anderson. You could use 5th or 6th edition of this book available in our library. And for practical classes, I recommend you Anderson Tannehill Pletcher as the base book, Computational Fluid Mechanics and Heat Transfer. And also you can find many other resources about aerodynamics in our library or in the internet. Aerodynamics is having already more than 100 years history, and it studies the magical forces which appear on airplanes and allow them to fly or allow them to resist to gravitational forces and take off. These magical forces we will study here in aerodynamics, and our lectures will allow you to understand how to relate force and flow properties happening around the aerodynamic body. History of aerodynamics accounts for more than 100 years of development, and many famous scientists contributed to it. Probably one of the most famous was Ludwig Prandtl, and we will study in this course many of theories he has developed. Here on my screen you can see several airplanes which were developed with advancement of aerodynamics. For example, you can see here Douglas DC-3. It's one of the most famous aircrafts of all times, and it was a low-speed subsonic transport designed at 1930s. Then next one, you can see Boeing 707, which already flew at high speed compressible regimes, and it allowed transportation of millions of passengers in the late 1950s. Then Bell X-1 was the first airplane flying faster than sound, and Lockheed F-104, which already flew with Mach 2, a huge advancement for time of 1950s. And with the development of computational method, it was possible to create airplanes which sustain long supersonic flights. For example, Raptor F-22 is one of the most perfect airplanes for supersonic flight regimes. And finally, you can see a blended wing body, which is theoretically one of the most performant aerodynamics bodies which could be created. And this could be a future of aviation. And of course, advances in aerodynamics are not just limited by applications to airplanes. You know that flow of gases and flow of air is also very important in other fields, for example, civil engineering, flow around buildings, application to automotive engineering, flow around cars, flow inside the engines. So there are many applications where aerodynamics plays an essential role. Now I would like to talk a bit about historical examples in aerodynamics. One of the first work we can find in the literature is so-called Newton's theory, which was developed by Isaac Newton in 17th, 18th century, and it was trying to describe movement of fluid around an obstacle. This model, as we might see on figure 1.1, is showing to us that fluid is moving undisturbed before it meets a body, and then suddenly it turns to an angle equal to the angle of the body. It was at that time an advanced theory, but after was evident that theory is completely inaccurate. However, in 20th century, with development of supersonic and hypersonic flow applications, there were found some similarities with the theory of Newton and the movement of supersonic gases. And this is one of the reasons why one of the theories of hypersonic flow movement is called Newtonian theory. We will study it at the end of gas dynamics in the chapter which talks about hypersonic flow applications. Another very famous study of aerodynamics is provided by Wright brothers at the United States, which built a wind tunnel in order to find the best profile of the wing and build flying airplane. This wind tunnel, as you might see from this picture, is consisting of test section where airfoils or wings were tested, and a fan which accelerated the flow in axial direction. One of the very important advancement in aerodynamics and gas dynamics is development of theory of shock waves. Shock waves are present in flow that are moving with the supersonic velocity with respect to a body. And such interaction of flow and the body creates a rapid change of flow characteristics and flow properties, which we can consider as discontinuity and we call as shock wave. Shock waves can be of different type. For example, here on the screen we can see an oblique shock wave which is inclined with respect to the flow direction. Also in gas dynamics we will meet with another type of shock waves, normal shock wave, and the combination of oblique and normal shock wave flow around supersonic blunt body is so-called bow shock wave. The bow shock wave you can see on my figure 1.4 flow around blunt re-entry body. Right. Actually, this is one other advancement in aerodynamics that is an answer on a question which should be the shape of re-entry body not to burn in the atmosphere. First of all, we understand that a rocket or shape of the rocket or shape of the re-entry body could be of a different shape. Depending on this shape, we can have different structure or flow around its body, and we will have different properties of heat exchange, of flow around the body and the surface by itself. A big advancement in a theory of supersonic flow was made with the development of blunt re-entry body theory, which is transforming or reconfiguring the balance between heat in the air. For example, here in figure 1.4, you can see on the upper part an oblique shock wave where there is a small heating of air after the shock wave, but since we preserve the same amount of energy in the flow, we will have larger heating of the body. The total energy will be same. In case of blunt re-entry body, we will have a different shape of shock wave. As a consequence, we will have larger heating of the air, and we will have a slower velocity of this air. And as a consequence of this low velocity and large heating of the air, we will have smaller heating of the body with respect to an oblique shock wave. Such flow structure can be observed experimentally. You can see it in the middle of my screen. And such flow structure can be observed also numerically by numerical simulation or computational fluid dynamics, which we also will study in the future. Next, we must talk about classification and practical objectives of aerodynamics. We see that when solid is interacting with liquid is fluid dynamics, when solids interacting with air is called aerodynamics, and interaction of solid body with gas in general is called gas dynamics. Also inside gas dynamics we include compressibility effects, so compressible aerodynamics is usually also called gas dynamics. Here is written what I just said you on the previous slide. And here is the scientist working on a gas dynamic laser, one of motivating picture which should help you to understand the importance of aerodynamics theoretically. Okay, here is the roadmap for chapter 1 of aerodynamics. Here we see definition of basic aerodynamic quantities like pressure, density, temperature, flow velocity, streamlines. We see how to quantify, how to find equation of these quantities. Then we see the source of aerodynamic forces and moments, and how to obtain them by integrating surface properties like pressure and shear stress. Then we will define the general reaction force and its division on lift, drag, axial normal components, and momentum coefficients. Then we will see how to calculate center of pressure on aerodynamic body. After doing this, we will find a way how to make dimensional analysis, which would help us to find relation between, for example, test of a model of an airplane in aerodynamic tunnel and real flight conditions. Then we will talk about fluid statistics, what happens when there is no flow. It's quite short topic. And at the end, we talk about types of fluid flows, continuum flows, inviscid, viscous flows, incompressible, compressible flows, subsonic, transonic, supersonic, and hypersonic regimes. It's a kind of a reminder for you, for people who had worked with fluid mechanics, for example, or fluid dynamics some time ago. For people who just finished fluid mechanics and fluid dynamics, this would be very, very simple topics. Okay, the first part of chapter 1 is fundamental aerodynamic variables. These fundamental aerodynamic variables are scalar or vector values. And maybe one of the most important is pressure is defined as the limit of ratio of force, elementary force on the elementary area relation. Pressure can be seen inside the fluid or on the body surface. Then we have definition of density, which is limit of mass differential by the volume differential. Density has dimension of kilogram per meter cubic. And temperature, which can be defined by the kinetic energy of gas through the Boltzmann coefficient. And also temperature can be defined by the equation of state of a gas. If you know, there is a relation written as pressure equal to density multiplied by gas constant multiplied by temperature, where temperature could be calculated from this equation. To use this equation, do not forget that we must have all quantities in C units, for example, pressure in Pascal, density in kilogram per meter cubic, gas constant in joule per Kelvin per kilogram, and temperature would be calculated in Kelvin. As a vector property, we have a flow velocity, which shows us direction of movement of fluid at any point. Probably, if you remember fluid mechanics, you know that this fluid velocity could be different for any point in space, as well as any scalar property like pressure, temperature, and density. Then we have definition of shear stress, which is related to viscosity. Here, shear stress would be proportional to dynamic viscosity coefficient multiplied by gradient of velocity in the direction normal to the wall, where y direction is direction of perpendicular to the wall of body. Usually, shear stress we have inside boundary layer, where velocity gradient has considerably high value. Outside of boundary layer, where velocity is approximately same everywhere, shear stress would be negligibly small with respect to pressure forces. Okay, once we talk about thermodynamic and aerodynamic properties, we can speak about aerodynamic forces and moments. What are these forces and moments? The source of aerodynamic forces and aerodynamic moments are pressure and shear stress distributed on the surface of the body. We know that pressure force is always perpendicular to the body surface and shear stress is tangential to the surface. Once we integrate, which we will see very soon, these forces will result in momentum and reaction. After we obtain reaction force, we can split it in various combinations of forces, which would be probably perpendicular forces. Here you can see on this screen there is a reaction force as a total of all influence of pressure and shear stress on my airfoil, and this reaction force could be split to lift, for example, and drag. Lift is L and the drag is denoted as D force. Lift and drag forces are perpendicular one to another. Lift force is a force which is also perpendicular to the infinite velocity. Here you can see it on figure 10. So lift perpendicular to V infinite, and since lift and drag are one perpendicular to another, drag is parallel to velocity vector. Then when we will work with aerodynamic quantities, sometimes it's useful to split reaction force to another pair of vectors, which are called normal force and axial force. Axial force is the force which is going parallel to the main chord of airfoil. The chord is the line, straight line, which joins the starting point of airfoil called leading edge and the final point of airfoil called the trailing edge. And parallel to axial force, we have a normal force. So perpendicular to axial force, we have a normal force. And it's also perpendicular to a chord. Transition between normal axial force and lift and drag force can be easily seen by trigonometric relations once we introduce angle between these pair of forces. As you can see, this angle is denoted as alpha. You can see this angle also between infinite velocity and direction of airfoil is alpha on the left. This alpha also can be seen between lift force and normal force. And because all these angles or forces are creating similar triangles, this alpha can be observed between axial force and drag force. As I already told you, the resultant force is R. So writing in vector form, we can have the following relation that R is L plus D, and it's same as N plus A vectors. Based on this vector relation, we can find the relation between lift, drag, axial, and normal force. For example, this relation between lift, how to calculate lift and drag when we know normal and axial forces are shown on this slide here. We can see that lift force must be or can be calculated by taking normal force value multiplied by cosine of alpha minus axial force multiplied by sine of alpha. And the drag force can be calculated as normal force multiplied by sine of alpha plus axial force multiplied by cosine of alpha. This can be also seen or visualized based on our schematic of forces, which you can see here. For example, let's see that lift force, how much would be when we take a normal force multiplying it by cosine of alpha. Let's see what it gives to us. I will make a projection on lift force direction. So my n multiplied by cosine of alpha would be this big vector starting at the origin of coordinates and finishing at the top. So it's bigger. It's bigger than my lift force, this first part, and cosine of alpha. So I need to subtract some value, this value which you can see on my screen, and this would be exactly axial force multiplied by sine of alpha. Let's make projection again to the direction of lift force. And here it is, since my axial force is going down, it will generate projection vector also going down. And this projection vector would be equal to A multiplied by sine of alpha. And it will be exactly the vector which I needed to subtract from my first vector and cosine alpha. As the result, I receive a lift force. So this is a sine of alpha. And for the drag force, we can do the same. We just need to project normal and axial force on direction of the drag force. So let's do this example here. Let's project normal force. This is, I will try to do it carefully. Okay, this is the projection line and this is the force. So I will denote it as n sine of alpha. So there is missing a big part, and this big part I will obtain projecting axial force on drag, and I will receive this big vector here. I will make it by another color just for better visualization. Okay, so this is my A cosine of alpha. When I summate this n sine alpha and a cosine alpha, I will receive my drag force. This is how transformation can be done, and such transformation can be provided also in reverse direction. From lift and drag forces, we can obtain normal and axial force. I hope you can do it by yourself. And in one of the videos in questionnaire of aerodynamics, which are an additional subjects or additional questions which were asked by students, I already explained this question. I hope you can find it by yourself. Aerodynamics is an applied science with many practical applications in engineering. No matter how elegant an aerodynamic theory may be, or how mathematically complex a number solution may be, or how sophisticated a aerodynamic experiment may be, all such efforts are usually aimed at one or more of the following practical objectives. First objective is prediction of forces and moments on and heat transfer to bodies moving through a fluid, usually through air. And the second objective is determination of flows moving internally through ducts. For example, we wish to calculate and measure flow properties inside the rocket or air-breathing jet engine to calculate engine thrust. So we need to know flow conditions in the test section, wind tunnel, we need to know how much fluid can flow through pipes under various conditions. And this aerodynamics allows us to do. This is the end of lecture 1, and thank you for attention.